This week on Developer Voices, we're looking at the future, as we often do, but not the future of programming per se. We're going to talk about how some very well-established ideas in programming are being used to accelerate the bleeding edge of chemistry. My guest this week is Professor Christian Schafmeister, and he's been working on a new implementation of Common Lisp to speed up the design of nanotechnology. Bits of this at times sound like science fiction, but it's very concrete. The plan is, next year, they're going to be building enzyme-sized machines that are being designed right now in a Jupyter notebook, in a REPL, in Lisp. You have to ask, why Lisp in this day and age? And we're going to get into that. Lisp still has a few features that more recent languages would struggle to emulate and might do well to emulate. To get there, we're going to have to go back and learn some of the most interesting chemistry I've heard about since school, so we better get cracking. I'm your host, Chris Jenkins. This is Developer Voices, and today's voice is Christian Schafmeister. I'm joined today by Professor Christian Schafmeister. How are you doing, Christian?
Great, doing great.
I'm glad to have you here. You are our first professor.
Oh.
Which feels very, very formal. Normally, we have a lot of people on this show who've picked up a lot of knowledge along the way, whereas you're steeped in a particular field, which isn't our usual wheelhouse. It's chemistry.
Yeah.
And
yes, indeed.
So we're going to talk about the language you've been building, but we really have to start with why you needed a language, because this is the closest I think we've got to science fiction on this show.
Yeah, so I've been developing something for the last 30 years where I want to be able to build machines on a molecular scale. So I have gone deep into organic chemistry, and I now teach organic chemistry. And we've been developing these molecules that are programmable, that are made out of building blocks, that are like rings. And when we snap them together, it's kind of like Lego. You can make molecules with different shapes, right. And they're complex. And so I have been developing software since I was 12. I was one of the kids who kind of hung out at Radio Shack and learned how to program in BASIC on a TRS-80. And I knew that I wanted to use software to design these molecules and that it would be very complex. And so I've been working towards both of those things in parallel over the last 30 years.
This is very cool. With a different chipset, that's where I was basically starting off from Radio Shack. We have a similar background.
Sure.
But we're not talking like we are talking nanotechnology, but these aren't nanobots. These are different kinds of chemical machines.
We are talking about nanotechnology. The things that we build are on the nanometer scale, but this is absolutely from the bottom up. We build things from molecules and build them up, and we know where every atom is in space. And I'm actually a Feynman awardee. I think it was in 2005. You'd have to look that up. But yeah, I have the Feynman Prize. And I've been funded for nanotechnology in the past.
This is cool. This is machines at the level of taking inspiration from enzymes, that kind of thing? Are we?
Yeah, that's really where we're kind of focused, because enzymes are the key technology that I believe human beings need to develop. Those are big molecules that can make other molecules that can make feedstocks for industry and fuel and take garbage and turn it into useful things and detoxify pollutants. All of that can be done by enzymes. We have a whole bunch of them that nature gives us, but they were evolved for the purposes of living things. There are so many chemical reactions that if we could create enzymes for them, we could solve every material problem that human beings have for all time to come. It's a fundamental technology that we need to develop.
You really see this as completely changing the world?
Absolutely. It's if we could make molecules that could build other molecules, then every problem, every physical material problem we have, we could solve.
Somewhere between shrinking chemistry professors down to the nanoscale. And
that would make us simpler. I don't know about that, but the essence is like an enzyme is a molecule that's large. It's got a pocket, and it organizes groups inside of it. So it acts like a little breadboard, like a little circuit. Another molecule will pop into that pocket, and there's push and pull of electrons. It's like a tiny it is the smallest electronic circuit, and it works for just a few picoseconds. And a new product emerges, and then another one goes in, and that gets repeated over and over again without the enzyme being modified at all. So it's the essence of life, and we can't do that in a rational sense right now at all as well as nature has done. Nature has millions of these enzymes that it's evolved over countless millions of years that can accelerate many reactions.
And is this? I'm just trying to understand for the background, right? Is this you're going to custom make an enzyme that takes some raw materials and builds a particular flurry of a molecule? Is it then that you'll have? Is there a larger structure beyond that? Are you going to fill a vial with some enzymes that take raw components and put them at level 1, and gradually the next enzyme in the chain builds up something more complex until you've got something on the physical scale recognizable as a thing?
Yeah, you've got it. Systems of these could build complex molecules. They can fix, here's a crazy example. One of the theories of aging is that basically sugar, glucose, cross-links proteins outside of our cells in what's called the extracellular matrix and stiffens up the tissue. I mean, that's known. That actually happens. And the cross-link is called glucosapane. And if we could make a specific little enzyme that could go in there and cleave those cross-links, you might be able to cure a lot of diseases of aging. I don't know if it turned back the clock, but it's one current hypothesis for how aging happens. That basically glucose cross-linking proteins, it's called the Maillard reaction. It's the basis of cooking. And that's what's basically happening to us over 60, 70, 80 years.
Right.
So if you can make an enzyme that could cleave those cross-links specifically without doing anything else, you might be able to treat a lot of diseases of aging.
And what's the timeline on this? So we can make these enzymes on a small scale right now. Is that right?
We can't design good ones. And it's difficult to make big molecules that can wrap around that can create pockets and wrap around smaller molecules. It's really difficult to do that.
But if we had the recipe, we'd know we could physically manufacture them.
Yeah, one recipe would be based on proteins. And there's a lot of people like writing software to design proteins like AlphaFold. You've heard of that. Rosetta is a software package that comes out of the University of Washington, David Baker's group. That has been developed over the last 30 years to design proteins. Proteins can do this kind of stuff. They are difficult to design with. My life's work is to come up with a more engineerable building block set. So proteins are sort of like bead necklaces or charm bracelets. Right. They have they're a long string. They have little charms on them, and the charms, some of them are really greasy, some of them love water, and nature has put them together in a particular order so they fold up into like a ball with little pockets on them, and that's how they create the pockets that can do the work. That folding process is a grand challenge of science, predicting how proteins fold. Now, the Rosetta and a lot of other people who have worked on, using software to read, pack the insides of proteins have been tremendously successful. But creating the intricate inside of a enzyme is really difficult to get it exactly right, because you have to control where groups are within, a tenth of a nanometer. AlphaFold has been a huge breakthrough in using deep learning to predict the folds of proteins that we don't know the three-dimensional shapes of. I've got a different approach. I thought, let's build building blocks that are just easier to design with in the first place. So instead of making a charm bracelet, a bead necklace, let's make little ladder, like rungs of ladders, and then snap them together through two connections at a time. So you make a bunch of rings that are fused together. You make things that snap together more like Lego than linking, beads on a necklace.
Right.
And then they're easier to design with. And then write software to design them.
So your idea is that you're going to have like a tray full of different building blocks and then figure out how to assemble them to make interesting enzymes. And this is where we're getting into, is it pronounced CANDO, which is a great acronym for Computer-Aided Design Nano, I've forgotten the O.
Computer-Aided Nanostructure Design and Optimization.
Right. So we're really on the level of CAD software for molecules.
Yeah. I've written this like 4 times. And I started out writing a CAD, graphical user interface sort of software. But every time I got something, my students came up with chemistry that it couldn't handle, and it required a redesign. And then I settled on, I'm just going to write a language and build a user interface on top of that.
Oh, right. Now here's where we get into language design. So at what point did you say this is going, what point did you say, I'm not going to be able to do it with the existing software that's out there. I need to build something custom?
I think I was writing it in Smalltalk at that time. And I had a really nice user interface, and my group figured out how to put what we call functional groups, sort of side chains off of each building block. And the way I was building the molecules just wasn't going to work with that. And so I just scrapped it and started over again. I spent a lot of time writing, chemistry requires performance. You're always doing things on lots of atoms that requires writing loops that do intricate things, and you need it to be very fast. So most of my stuff was written in C++, and then I would hook that into other languages. For the longest time, I was using Python, but the interop between Python and C++ and managing lifetimes of objects became very troublesome. So I came up with another way, and that's what the current CANDO and the Common Lisp clasp that it's built on. That's where that came from.
And this is an unusual route, particularly these days, I think, to go from Smalltalk to Common Lisp. What year are we talking when you did this?
Probably about 2005, 2006. Okay.
That still counts as relatively recent in the grand scheme of things. Why Common Lisp?
So I was looking around at the time for a language that would allow exploratory programming. I knew I needed automatic memory management. I needed performance. That was the key thing, performance. And I had this core of chemistry code that was written in C++. It's about 250,000 lines of code at that point. And I had it all hooked into Python, was running into a lot of trouble. This is back in the Python, before Python 3, and was running into a lot of trouble maintaining that. And a friend of mine was at NASA, and he'd worked a lot with Common Lisp and said, you should check out this language. I was using XML a lot for serializing data at the time, so I started getting into this idea of nested scope in the language, and I started implementing a Lisp in my C++ and found that it worked very well with chemistry ideas that I was trying to implement. So I moved on from there. I don't want to monopolize the conversation, so I'm going to pause.
No, it's your job to monopolize the conversation. But so what is it about Lisp that lends itself to chemistry, though? I can't quite see that.
So it's really easy to express graphs and trees and linear sequences in Lisp with parentheses. I don't know, it just flowed really well. So I had all the C++ code. I was writing a Lisp interpreter and started to write, basically implementing my own Lisp. And I didn't go very far, and I realized it was crazy to try and implement my own language because I developed in a lot of languages. I know how difficult that is to get that right. So I just looked at what kind of Lisp implementations were out there, and there's Scheme, there's Common Lisp, Emacs is based on Lisp.
Yeah,
there's a couple of them out there, but I wanted one that was kind of full-featured, battle-tested, had been used to implement large programming systems, and like Common Lisp is used in the Google Flights. The engine behind that is all implemented in Common Lisp. And so I thought, Scheme's got this specification that's like 25 pages. Common Lisp has this specification that's like 4 inches thick. I'll go with the 4-inch thick specification.
Not the decision I would have made, just on those metrics.
I do have a tendency of always taking the hard road on things. But
you don't become a professor if you don't like reading, right?
I guess, yeah. So there are several implementations of Common Lisp, and one of them is implemented in C. This is called Embedded Common Lisp, or ECL. Much of that is written in Common Lisp itself. It's self-hosting, and it has a lot of C core to do the lower level stuff.
Right.
So I just took that's a GPL software package. It's got a GPL license on it. Or an LGPL license. So I took the Common Lisp code from ECL and just started writing my Lisp interpreter so that it would execute that. And I just kept going and executing more and more of it. And my Lisp turned into a Common Lisp implementation.
Oh, I see. Okay.
I also have good C++ interoperation. So I was doing a lot of C++ template programming, and I implemented something like Boost Python to integrate C++ and the Lisp. And then I integrated the LLVM compiler library, exposed that to the Lisp, and then I started writing the backend to generate LLVM-IR using the LLVM C++ API. And that's how it all grew.
Why that step? Because I can see why you need C++ access. Why go into the LLVM part?
Performance.
Just performance.
With LLVM, I can get native code compilation. And without that, I would always have an interpreter.
Right. So you said kind of not cannibalized, but stood on the shoulders of an existing Common Lisp implementation.
Yes, but the developer of ECL, Daniel, is, we hang out on IRC and we fix bugs in each other's systems because we share a lot of code base. It's been great working with that community and the larger Common Lisp community as well.
So, what circumstances do you think this is the right choice? I mean, if someone else is in your position with a large C++ code base, when would taking your path be a sensible one?
Well, I would hook it into Clasp. I think it's a great tool for exposing C++ code in a high level language that has dynamic memory and a bunch of other features. I've hooked in DNA sequencing analysis libraries like CCAN, and it's very easy to integrate C++ code with Clasp, and that gives you access to all the Common Lisp libraries.
I would have thought that, I mean, anytime I think of programming in the science world, I think of Python. Are you losing something by moving away from Python in this?
Yeah, Common Lisp, if you take Python code and you take all the functions and you just take the parenthesis for the function call, foo, open parenthesis, arguments, close parenthesis, take the name of the function, move it into after the first parenthesis, remove the commas, and that's basically Lisp. It's not that big a change. Then you have all these functions that give you, string handling, file handling, all sorts of stuff like that. And you have a full language there. I mean, it's really not that different from working in Python. It's just that it compiles to native code, and it's Common Lisp was developed, and it's a standard language. So it has a standard that was developed back in the 80s, and it's a forever language. Like the code that I wrote 10 years ago in Lisp, I'm using now. And libraries that I use, some of them have been written over, the last couple of decades, and there's a large library base of Common Lisp that works because the language doesn't need to constantly change. There's a standard, and everyone writes to the standard. There's multiple implementations, so everyone writes code that works on a large number of standards, and it's there's a philosophy of writing things properly rather than writing them just so that they work or they work now.
Yeah. I gather a lot of software in the science world suffers from that problem. Understandably, because most people in the science world aren't primarily programmers, right?
They're not. And there's a tendency to write stuff that does what you need to get the paper out, and then it rots. Then it rots and dies.
But I got to ask you that question again, because so there's an argument that you take any programming language and strip the syntax out and you end up with Lisp, because Lisp is the programming language with almost no syntax. But Python isn't just the syntax and the core library functions. It's this whole ecosystem of science packages, particularly mathematics. Are you missing that in your Common Lisp world?
Absolutely. There is a lot of momentum behind it. But if I started writing this in Python, I would be really bogged down right now with, you can't write loops in Python and expect them to run quickly. And when you write I work with a lot of three-dimensional data. I've got a molecule, it's three-dimensional XYZ coordinates, and I need to put water molecules around it. So I have to do a loop across X, I have to do a loop and wrapped in a loop across Y, wrapped in a loop across Z. I've got like 3 nested loops. And then inside of that, I've got it doing something really complicated, like figuring out if a water molecule is overlapping any atoms in my molecule. If you write that in Python, it's going to take an hour to run. In Common Lisp, with a little bit of C++ assistance, it happens in a fraction of a second. I can't give up performance. Time is the most valuable thing to me. So I'll invest a lot of time in developing the software if it runs quickly when I need it to. And I'm now running things on large clusters, distributed computing across large clusters that would take years of time when it's run on a single CPU.
Yeah, I can see that. Like Python's more than fast enough for the average web server, but when you're folding proteins in 3D space, I can see that every nanosecond counts. Right?
I've been around. I've programmed since I was 12, so more than 40 years, and all the Python that I wrote back in the 90s is gone, dead. When they changed to Python 3, I didn't upgrade all those libraries, and it's now gone. So all of that was kind of taken away from me. I don't want that to happen again. So I'm only developing now in forever languages that are going to be around for till 20, 30, 40, 50, 100 years from now.
It's one of the few languages where I could predict the syntax won't change much between now and then.
Yeah, and I have the rare experience of writing software that's been used for more than 30 years. Before I started graduate school, I wrote a program called Leap, which is kind of the front end for Amber, which is one of the large academic molecular dynamics packages.
Right.
It simulates the motions of proteins in DNA in research. And it comes out of the University of California in San Francisco. So I was given the job before I started school to write a front end for it. So it would make it easy for researchers to load in their proteins and set up the calculations to run on this. At the time, it was written in Fortran software. Now it's got the fastest GPU implementation, but my software Leap is still being used today. Probably some significant percentage of the world's biomolecular simulations go through Leap every day and have for the last 30 years. That thing was written in C, and they've tried to replace it. Like the Amber community has tried to replace it, I think twice, and have not succeeded because it does an essential, difficult job really well. The downside is it hasn't been improved very much in 30 years because it's difficult for people to get into the way it was written.
Well, so that raises a question of collaboration. You're writing this software in Common Lisp. Is, again, to an audience that's probably, if they know programming at all, probably knows Python, I'm guessing. A team of technically astute chemists. How are you finding the user experience, and how are you making it usable for people?
We have there's really powerful tooling based on Common Lisp tooling software. Let me rephrase that. So there's a software package in Common Lisp called Slime, which runs in Emacs.
Yep.
And lets you connect into a running Common Lisp instance and develop code. It's got an interactive debugger. It's got auto completion. It has everything you want. It's a really beautiful programming environment, sort of integrated development environment. That's all text-based, working in Emacs. So we fully support Slime. I use it every day. I've got it open right now. It's one of the most wonderful, interactive, exploratory programming experiences I think you'll find. Now, I haven't used a lot of modern IDEs for C++ or Python, so maybe I'm talking out of my hat there, but it is a really fluid programming experience. So we have that. We've also developed a Jupyter kernel based in that runs Clasp or Can-Do. So it's got widgets for doing displaying molecules and graphs and things like that.
Okay, so you can open a Jupyter notebook and type in some Common Lisp and see your molecule and that kind of thing.
Yep, exactly.
Well,
my usual development environment is to have, I've got Can-Do running, I've got a Jupyter notebook instance talking to it, and I've also got Slime running in Emacs, also talking to it. I'm developing code in Slime. I'm seeing the effects, the output in the Jupyter Lab environment, and that's how I get my work done.
Do you know, if that plays out the way I'm seeing it in my head, I think a lot of modern IDEs and more modern languages would struggle to match that. If you've got the mixture of the interactive programming experience and the live visualization, there aren't many languages that do that well, assuming yours does.
That's a good point. I really hadn't considered it. I I was really inspired by the sorry, what is that new Apple language that
Swift?
Yeah, Swift. So when they first demoed Swift, they had this sort of interactive programming, environment. I love that demo. I'm really inspired by, the small talk interactive programming environment. Slime is really great. I want something where I can be talking to the programming environment, add functions, change everything about it. I want to be able to change class. I need to be able to change class definitions, functions, add generic functions that will add new functionality. I want to do all that stuff interactively, and that's what I have with this system.
Yeah. Yeah. I think to that, I can say I think Lisp is the only language where I've genuinely felt like I'm having a conversation with the computer. That dynamic, interactive experience.
Yeah, that's an interesting way to put it. I hadn't really considered it, but yeah, I would agree. It is really. I really enjoy programming in it.
That's cool. I have to. This is a very nerdy question, but I'm allowed to ask those. I have to ask. So you're looking at doing an interactive Lisp with C for the fast bits as bindings. Did you ever consider just doing an Emacs Lisp?
When I was first getting into Lisp, I was a little confused about what was what, and I thought that would be an option, but it doesn't have the native compilation. It's a reference implementation of a language. And so I decided, no, I'm going with a standard.
Fair enough. Okay. In that case, let's talk about the this performance bridge. So I'm assuming you've got C++ where it needs to be really, really fast. And I'm assuming you're, as far as possible, you're in Lisp land for the convenience, interactivity, high-level preferred way of programming. Tell me about the bridge and when you know it's time to put something on this side or that side of the bridge.
Yeah, now I usually start, I don't know, I've got a really, at this point, I've got an intuitive sense of when I really need speed and when I can get away with that. I do all the sort of low-level C++ work in implementing the Common Lisp. So I do a lot of C++ development, a lot of C++ template programming, and I think I'm pretty good at it now. We implemented LLVM as the backend so that we can generate native code, and that code runs pretty well, but I still can't implement something in Common Lisp and have it run as efficiently as it would if I implemented in C++, because Common Lisp does try and make everything safe and everything's wrapped in most of the objects are wrapped in wrappers. So that slows things down. We've now implemented a bytecode compiler in CLASP to sort of deal with the slow compilation of LLVM. Which is a great library, by the way. My train of thought is just derailed. Could you reiterate the question?
So there's like, you've got Lisp in programmer space where it's nice, and C in computer space where it's fast.
Right.
Which parts of that go on which side of the line?
Profiling.
Okay.
So because we generate LLVMIR, we can compile everything to LLVMIR down to native code, and it all turns into object files and, basic Unix elf mock sort of stuff. So we can profile the Common Lisp against the C++ perfectly using perf or using dtrace on the Mac. And we generate flame charts, and I can see where time is being spent in the code. So it's profiling.
Right. How much work was it to get that working?
A lot, because it's really fussy. Especially the JITted code, the just-in-time compiled stuff that we're generating all the time. to get the names accessible for the profiling tools, had to futz around with a lot. They basically they had to solve the same problem for JavaScript on the browsers. So we used those mechanisms once I learned about them. But yeah, we can profile everything on an even level, and then depending on where time is being spent, I will move stuff into C++ if I need to.
Okay, so it's manual. But can you do that all while your same process is running?
Yeah.
So you can take a function that's running too slowly and interactively update it with a C++ definition?
Oh.
Or interactively compile it to C++ on demand, or?
No. Changing the C++ code means rebuild of the system.
Okay.
That takes about 5 minutes, and then restart everything and reload everything. Yeah.
Okay. So this is another reason to keep certain things in Lisp space for the interactive reloading without restarting thing.
Yeah.
Which really puts me in mind of Crash Bandicoot. Do you remember that video game?
Yeah. It was very inspirational.
Yeah, that was a good sales pitch for Lisp back in the day.
Yeah. So I do most of my development in Lisp. And it's only when profiling shows me that I've got a problem that I move it into C++.
Okay.
Or rejigger it to get things into C++.
Okay, then maybe we should talk a bit more about what's good in Lisp space. So what are the poster children features of Lisp? Macros. Are you using the macro system much?
Some. You have to use that carefully. It's a powerful, pointy tool. But yeah, it lets you sort of write your own flavors language. Yeah, we do use it. The macro system is really the basis of Lisp. All the stuff that makes it really powerful uses the macro system. So in that sense, we're using it all the time. But writing my own macros, that's pretty, I don't do that often.
Okay. What about the reader system?
It's another powerful tool. I have a recent use case for that. We have all of our arrays, we have specialized arrays. So for floats and doubles and integers, where they're just represented in compact data in memory.
Okay.
When I need to serialize large, complex data structures to disk and then load them back in for running calculations. We could talk about, the save Lisp and die thing. But the saving these large vectors, I'm using the Lisp printer and reader to dump these complex data structures to disk and then load them back in. And that is fairly slow. It's like Pickle, or it's like using JSON, but you can have internal references in the data structure.
So you can build up circular graphs.
Yes.
Yeah.
Yes. And that's an absolute necessity for what we have, because molecules are graphs.
Yeah. Like it or not, it's cyclical. Yeah.
Yep. And so it handles all that really well. But writing out the arrays was taking a lot of time. So what I did is I just turned this 8-bit data into 6-bit data that's human readable, just using 6-bit characters. And I write out this stream of characters to represent, the compact array. And I wrote a reader macro that, when it detects the reader macro characters, just reads in that 6-bit data and turns it into a 8-bit data structure in memory, and took my load times for these things from 10 minutes down to 30 seconds.
Nice. Which must come into play when you're writing C++ and having to reboot the world.
Mm-hmm.
Right. So do you have a perfect between session thing? Can you, when you're working with Lisp, you end up with this kind of working memory of where you're at. Can you flush that entire thing reliably to disk, reboot, and bring it back and be exactly where you were?
Yes. Yeah. So one of the really remarkable features of Lisp is this idea of save Lisp and die. where you just checkpoint all of them. You do all your work. You get your memory all set up to. You load all your files. You get everything set up to do something, and then you say, okay, save all this memory, and then later on start up the Common Lisp system, loading that memory, and be right back where you left off. Yeah, so I implemented that feature in Clasp, and I can load 100 megabytes of complex data structures to do a complex design calculation, and then save the thing to disk, and then start that up again in less than 4 seconds.
That's a rare feature these days, right? Because most programming languages, you can't checkpoint the state of the program.
Yep.
How much work was it to implement that?
You have to have a really good understanding of how the memory's laid out, and how our garbage collection works. So we support precise garbage collection. So I know where every pointer is in memory. And so it's just a matter of keeping track of all that stuff, writing it all into a block of memory, dumping that to disk, and then loading that back into memory, and then feeding it back to the garbage collector, which will put it wherever it wants to in memory, and then fixing up all those internal pointers. And that the memory survives that round trip.
Okay.
It's pretty complicated and fussy, but it's working. And what else can I say about it?
Is it reliable?
It's working perfectly. If one pointer was out of place, it would crash the system within moments. I have a memory test tool that will exhaustively check that every pointer is pointing to a valid object, and that gives me a lot of confidence that everything's fine. What we can't carry across that are like, it's got to shut down all threads, all but the main thread, and it has to close all file handles. But that's not as big a problem as you'd think.
Why not? Because I would think.
Well, for the stuff that I need to do, it's not. I can generate a memory image that we start up the Jupyter Lab environment, where we load all the packages that we need for Jupyter Lab to run, and then start up Jupyter Lab, and it first time to plot is less than 2 seconds.
Okay, fair enough. That makes me think. You mentioned the word threads, and I can't quite see. I can see how you've got a requirement for parallel processing and threading. How does that fit into a hybrid Lisp C++ model?
How does that fit? So we have Common Lisp has a standard. It's also got several libraries that have become de facto standards. Like Bordeaux threads is the de facto standard for creating threads, taking them down, communicating, setting up, locks between them. And we use that to do multi-threaded programming. Built on top of that are convenience libraries like L-parallels, where you can just do a parallel map. Common Lisp has lists and list comprehension, so I can map over a list. Blah.
Classic tongue twister, Lisp and Lisp.
Yeah. L-parallels let you parallel map over a list, so I can just give it a list of work, and it will allocate that to multiple threads, and I don't have to think about it. That's what I do.
Again, the advantage of working mostly in a higher level language.
Yeah. And when I'm doing that, I'm doing these design calculations. I've got a 28 core machine, and it's using 26 of them flat out. I get like 80-90% utilization of all the CPUs when I'm doing this design calculations.
That must be speeding up the high level chemistry task a hell of a lot.
Tremendously.
Nice. Okay, so zooming back out then, where is this tool going to take the research?
We are starting to design molecules now to be therapeutics and catalysts. We're doing that now. That's where we needed to go. So we're essentially there. It has taken a long time, and I really just got the high-level design calculations working in the last couple of months.
Okay. And so does that put you in a place where, I mean, the people using this, are they saying to themselves, I think this would be a great model. I think this would be a great enzyme to build. I think it will have these pieces. Are they working like a Lego designer, or are they Monte Carloing a number of things and testing which one works? Or
the people who are using this are basically me right now.
Okay. Okay.
And what are we doing? Let me talk to them. Okay. What we're doing is a lot of catalysts have metals at their heart, like metal atoms, like
Right.
rhodium and palladium and platinum. And so you say, okay, I got a palladium atom and I want to have groups that attach to it, hold it in place, and leave a space near it that another molecule can come in and get, interact with that metal, touch it. So you say, I need a group here, I need a group here, and here, and here. And then you say, okay, find me a scaffold that can hold those groups in place. And the scaffold is built out of our building blocks. And so the software goes and tries lots of different scaffolds, Monte Carlo search through design space, and tries to find the ones that can hold the groups in the right constellation.
Is this into the realms of things like, I don't know, genetic algorithms and that kind of stuff?
You can use those as search algorithms. I'm using Monte Carlo. It's the simplest, most powerful, elegant algorithm to do this. You have a scoring function, you generate possibilities, and you just crank on them on as many CPUs as you can get your hands on.
And possibly to finish off, it's very hard to predict the future. It's very hard to predict timescales. But at what point will we see a clasp-designed molecule being made in a lab? As an
I'm hoping in the next year.
In the next year?
Not hoping. I'm doing it in the next year.
Okay.
So the other thing is, I'm funded by the Department of Defense, and I've got a company that's developing this technology, and we've developed the way to synthesize these molecules. We've made thousands of them in the last 3 years. So we can make these molecules very quickly and easily. It takes a day to make any reasonably sized molecules. It takes 1 or 2 days to make them, and we're doing this on robots. The problem now is, which ones do we make? At my company, we're making millions. We're putting them together into millions of different configurations, essentially at random, and then throwing them at the wall to see what sticks.
Right.
The software, those are our hands. We can make those things. The software is meant to be our eyes so that we could see and predict what to make. So I'm bringing that online now.
Right. Okay, so the search space is potentially so vast. That's the problem we're solving.
Vast. I mean, in theory, we have thousands of building blocks. In practice, right now, we have 40. You put 4 of those building blocks together in a sequence. That's a very small thing, but it could be a drug. So then you've got 40 to the power of 4 different shapes that you can make of just that small configuration. Okay. You can either try and make some subset of them and throw them at the wall and see what sticks, or you can try and design them in software. That's what CANDO is for, is to design them.
Right.
I don't know how well it's going to work. It's an experiment.
Yeah. Well, you're in the research business. Someone else can commercialize it. And eventually, what will we have? Fields of Schafmeister wheat? Or I'm trying to imagine the future that you're heading towards.
The first one is new therapeutics.
Right. Medicines.
Treat disease. New diagnostics to recognize emerging biological threats. Catalysts that can accelerate reactions and turn cheap starting materials into valuable products.
I have to ask then, if you've got something like this biological machine that manufactures drugs or manufactures useful things out of raw materials, if we see it, I mean, I'm just trying to think, like war zones, for instance, aid, outbreaks of viruses. Will these things be able to manufacture things in the field if we find them?
This is kind of long-term science fiction stuff.
Well, we're stretching out to the end of the podcast, so give me some sci-fi.
This is potentially, yes, we can rapidly build these molecules, and if we can rapidly design them, then yes, you could build things in the field. There's a lot of machinery that goes into this. It's not the first thing I'm going after. I'm really focused on is the basic capability. Can we design a molecule that does what we want when we want to make new therapeutics, new molecules that can wrap around proteins and act as diagnostics, or accelerate reactions, or create like channels that can purify single molecules out of mixtures? Like, could we pull lithium out of seawater or uranium out of seawater? You could imagine membranes that could just selectively pass uranium and keep all the sodium and lithium and potassium in seawater out. And then you could pull metals out of seawater, and it would be a lot less environmentally damaging than mining.
Yeah. Yeah. Plus, presumably, like dealing with pollution as well.
Exactly. I mean, when we can build things in the molecular scale like that with intent, with rational design, we can solve a lot of our problems. That's where I'm working. That's what I'm working towards.
Yeah, I can totally see the potential, and I'm quite pleased that there's Lisp somewhere in that future.
Yeah, it's a fun programming environment to develop this stuff in.
Well, I hope it goes well.
Yeah.
Christian, thanks very much for telling us all about it.
Chris, thank you for taking the time in.
Cheers. Thank you, Christian. Now, you'll have only noticed this if you've been watching this episode on YouTube, but throughout that conversation, Christian was drinking coffee out of a lab measuring beaker, which is brilliant, very on brand for a chemist. If nanomachines turn out to be the future of Lisp, remember you heard it here first. So please take a moment to like and subscribe, share with a friend, rate, post it to the social, all those good things. I appreciate the feedback and the support. It's also worth saying that this particular episode only happened because Christian got in touch with me and said, I've got an interesting programming topic that you might like. So if you have an interesting programming topic that I might like, my contact details are in the show notes, as always. And with that, I will leave you for now. I've been your host, Chris Jenkins. This has been Developer Voices with Christian Schafmeister. Thanks for listening.